Real-time simulation of direct torque control of BLDC motor drive using Opal-RT simulator. Abstract: This paper presents real-time simulation of direct torque control of brushless DC motor drive using Opal-RT simulator. The BLDC motor, which is not having brushes, has minimum losses which can be largely used in industries. The control of BLDC based upon various conventional methods which are used to control of AC machines. In this paper, the mathematical model of BLDC motor and torque control method used is based upon position of rotor, which gives proper orientation of rotor. This signal is gives to controller, which again gives to selecting switching table. Again, by proper selection of switching, the signal is sent to three-phase inverter, which then rotates the motor, and torque control can be achieved. Also, the real-time simulation can be achieved by using Opal-RT simulator OP4501. The simulation results and real-time results are obtained by using FPGA card and at time step. Index terms: brushless DC motor, direct torque control, torque ripple, switching frequencies, common mode voltage, real-time simulation, Opal-RT simulator. Introduction. In recent years, variable speed drives equipped with BLDC motors are extensively integrated into various applications ranging from servos to traction drives. Compared to black, it is relatively low cost, since it has shorter end windings and does not require precision position sensor encoders. Therefore, in general, BLDC drives are relatively low cost. The main advantages of the BLDC motors can be listed as follows: low noise, low inertia, high efficiency, high power density, more starting torque, large speed ranges. Speed and torque characteristics are linear. They operate in any condition and having minimum maintenance. In between the control strategies that exhibit a high torque dynamic, the Dtc method is mostly used for induction motor drives. The direct control is achieved by inverter switching pattern for control of electromagnetic torque and stator flux. Conventionally, speed control of BLDC drive is doing hysteresis controller. But recently Dtc has been employed for the BLDC drive. In Dtc, relationship is established between the torque responses. It gets better dynamic performance than conventional control methods that are less sensitive to parameter variations and simpler to implement. Electric vehicles have recently received many attentions from researchers due to their advantages over the conventional use of non-renewable sources. Electric vehicle reduces the pollution that subsidies to climate change and smog, improving public health and reducing ecological damage. 2. Block diagram of topology. The block diagram for Dtc control of BLDC motor drive is as shown in figure 1. From the BLDC motor, flux and torque reference is taken, that is compared with estimated value of torque and flux. Depending upon this, hysteresis controller applied the parameter for voltage space vectors that are applied to BLDC motor with the help of inverter, and estimated flux here voltage space vectors that are being applied to BLDC motor. By selection of voltage vectors, flux trajectory, i.e. circle or hexagon, is produced. In this technique, conditions of intensity switches are resolved straightforwardly by the determined and reference torque and transition signals. This is accomplished by utilizing exchanging table, the contribution of which are torque, stator motion blunder, and stator transition determined mistake, which is isolated into 6 parts of 60 degrees. The switching table output is applied to inverter, which depends on the error signals. For energy saving in industry, there is increase in use of variable speed drives. Initially, direct current machines are controlled by decoupled nature of flux and torque, then field-oriented control and Dtc methods are developed. Also, these methods then used for control of AC machines. In field-oriented control method, current controller and ability to know just sector in which stator flux linkage space vector is varied, rather exact position of vectors. In Dtc, the current controller is absent. The main principle of Dtc is to calculate instantaneous torque parameter depends on stator flux vectors. In BLDC motor, when forward active voltage vectors are applied, then stator flux linkage vectors move away from rotor flux vector. This increases the torque parameter because of torque angle increases. This means that when zero or backward active voltage space vectors are applied, then torque angle decreases. The current and voltage is converted into Parkes transformation, which is used to calculate stator flux linkage, is given by equations. Voltage and current equations WRT to stationary frame of reference. There are a few special features of Dtc control that can be summarized as follows. No feedback current control. No traditional PWM algorithm is applied. No vector transformation as in vector control. Feedback signal processing is somewhat similar to stator flux-oriented vector control. Hysteresis band control generates flux and torque ripple, and switching frequency is not constant, like hysteresis band current control. 3. Simulation and simulation results. A simulation of direct torque control of BLDC motor drive. The simulation model for DTC of BLDC motor drive is shown in figure. The overall system consists of two loops for torque and stator flux. The stator flux and torque tie is reference value is compared with actual value taken from motor stationary reference frame model, and from this errors are calculated for analysis. The errors then given to hysteresis current controller. Depending upon this, from current controller results are combining with position of stator flux and it making switching selection table. The DTC method requires calculation of stator flux and torque, which are obtained by two different phase current and state of an inverter as in figure 6. As transistors in inverter are switched to keep torque and flux with their hysteresis band, due to this switching losses are relatively low. Here, figure 6 shows that the torque is estimated from reference speed and actual speed, which is calculated as shown in simulation model, figure 6. IJERT.7 simulation model for reference speed generation. The back EMF is calculate from the formula where EAEB and EC are back EMFs as shown in figure 8. Where EAEB and EC are back EMFs, which is simulated in model as. From back EMF the ABC reference coordinate is converted into alpha-beta reference frame for calculation of alpha from given IE rotor angle. Figure 9 again, speed is calculated to torque estimation, then pulses are generated which is fed to inverter. Following figure 10 to 12 shows the simulation results corresponding to the steady state operation of the BLDC motor under the proposed DTC. The waveforms show the electromagnetic torque, common mode voltage and phase currents. The figure 5.9 shows torque/time characteristics of BLDC motor with no load. As the speed reaches to its steady state position, the torque remain constant. Phase currents are sinusoidal in nature and there is phase difference of 120 degrees between each other. Phase current waveforms for three-phase BLDC motor is as shown in figure 5.11. Figure 12 current waveform. Figure 13 shows the no-load speed of the BLDC motor. Here reference speed is taken as 1000 rpm, the motor reaches the reference speed at t equals 0.14 s and remains steady afterward. In this control the desired speed of the motor is achieved very smoothly, and this gives basic idea and information about the speed control of the BLDC motor for various applications. B. Real-time simulation. Digital simulators are evolved from analog simulator as simulation tools in past decades. It is carried out by using modern computer technologies. It requires less cost and increases the performance. Nowadays, the digital simulators are used widely in a number of industries because of it can be used virtually and there is no need for hardware prototype. The results are calculated before applying to real hardware model. In the real-time simulation, it depends on automatic code generation, which played a very important role in many engineering field and applications, such as industrial motor drive design, power grid statistical protection tests and complex robotic controller design. From the last 3 decades real-time simulators are used in power system and electrical drives. Simulation has major role in development of layout of power system transmission to motor drive optimization and plays critical role for large number of application. As the power system is a highly complex system, also it is highly nonlinear in nature. By using a sophisticated controller, it is very complicated to run the system. So that the real-time simulation gives many advantages. The advantages of using real-time simulation are as 1. Reduces the time. 2. Cost reduction. 3. Increases complexity and flexibility. 4. Reduces risks. In 1997 Jean Belanger and Lisa Laforce founded Opal-RT Technologies. In earlier it used in Canada ARM and Canada Space Agency. Then it is used, in power grid simulators, electrical vehicles. After few years in 2016 the Op-40 200 simulator for power electronics, electric drive and other real-time applications. Op-40 510RT Lab Simulator, provided by Opal-RT Technologies. The host PC is generating the real-time executables codes, also it modifies the real-time parameters and record the data received from simulator. The host PC and simulator are connected via Ethernet LAN connection as shown in figure 14. Figure 14. RT Lab Simulator, Op-40 510, with host computerized used to support the real-time realization of the complicated combined system. The host PC is generating the real-time executables codes, also it modifies the real-time parameters and record the data received from simulator. The host PC and simulator are connected via Ethernet LAN connection as shown in figure 14. To run the Simulink model with Opal-RT software and hardware, the following main steps has to be follow. 1. Open the model. 2. Edit the model in MATLAB. 3. Compilation. 4 assign nodes. 5 synchronization mode. 6 loading. 7 execution. 8 reset. The Opal-RT used in following field: electrical power systems, electrical power electronics, aerospace and defense, automotive, academic and research. C. Real-time implementation for direct torque control of BLDC motor drive. I software synchronization. The MATLAB simulation diagram for DTC of BLDC motor drive is shown in figure 15. To run this simulation model into real-time simulator, here we have to transform the simulation in two subsystems, i.e. SM main and SC console, as shown in figure 15. Figure 15 complete real-time Simulink model of DTC of BLDC drive. SM_main subsystem consists of main simulation model input-output blocks, pulse generators, torque estimation block, speed and sector selector block as shown in figure 16. SC_console subsystem consists of user interface blocks like scope, display, etc. as shown in figure 17. Console subsystem is available for the user while the simulation model is running. In the subsystem, OPCOM block is used for the communication purpose between master subsystem and console subsystem. Figure 17 console subsystem of real-time Simulink. The RT Lab generated SC_console block is shown in figure 18 below. It is running in RT Lab simulator, which is generated after the following through execution steps. SC console consists of various scopes. Figure 18 RT Lab generated SC_console block. Real-time simulation results. These are the results are obtained using Opal-RT Lab of DTC of brushless DC drive at speed 1500 rpm and torque 0.5 nanometers r as. The following figure 19 shows stator phase current of BLDC motor. The phase current is seen on graph is only phase A current. Figure 19 phase current of BLDC motor. Figure 20 back EMF generated by motor. The motor generates back EMF shows in figure 20, which is used for calculation of estimated speed. The back EMF is seen on graph with respect to time. The switching pattern generated by hysteresis controller by referring value of torque, phase currents, and position of rotor is seen in graph as shown in figure 21. The switching pattern shown is only for phase A, i.e. for one leg of inverter, which is then runs the BLDC motor. Figure 21 switching pattern. Figure 22 electromechanical torque. The electromechanical torque of BLDC motor is shown in figure 22. The figure 23 shows common mode voltage, which is calculated as 2 hardware synchronization. In hardware synchronization is done on an external hardware timer. For this some blocks are added in software synchronize model, i.e. op control, op-write, and analog out, as we using analog output signal which has to be given to the I/O port type board, TE0741. It is then given to the Opal-RT through connectors. Op control block is used to set the simulation state on the card. OPCOM block specifies communication between master and console subsystem. Analog out block sends analog signals to target simulator by using board TE0741. The figure 24 shows complete simulation diagram for hardware synchronization of DTC of BLDC motor drive. Figure 24 simulation diagram of hardware synchronized model. The SC_main subsystem for hardware synchronized model is shown in figure 25 below, which has main simulation model, op control block, op-write block, and analog out block. The SC_main subsystem for hardware synchronized model is shown in figure 25 below, which has main simulation model, op control block, op-write block, and analog out block. Figure 25 SM_main subsystem of hardware synchronized model. Figure 25 SM_main subsystem of hardware synchronized model. The SC_console subsystem and RT Lab generated console subsystem is shown in figure 16 and figure 17 respectively. Figure 26. The overall system. The figure 26 shows overall system which having host computer, Opal-RT simulator, and the output is seen on digital oscilloscope. The SC console subsystem and RT Lab generated console subsystem is shown in figure 16 and figure 17 respectively. Figure 26 the overall system. The figure 26 shows overall system which having host computer, Opal-RT simulator, and the output is seen on digital oscilloscope. The output waveforms on digital oscilloscope are shown in following figures. The waveform for phase current, IA, is shown in figure 27 and figure 28 shows switching for phase A. For conclusion. In Dtc method, between estimated and actual values of flux and torque has error. For reducing the torque and speed errors we have to control different state of inverter is possible. With comparison with other conventional methods, This method minimizes steady-state errors by controlling estimated torque of high-performance motor drive. Also, the real-time simulation is performed using Opal-RT Figure .30 back EMF, EA, Figure 31 electromagnetic torque OP4510. First we analyzed the results using software synchronized method and the results also analyzed in digital oscilloscope using hardware synchronized method. Due to Dtc method errors between estimated and actual values of flux and torque, it is possible to control directly different state of inverter to reduce torque and flux errors. The simulated results help to determine precise control of estimated torque, and hence it leads to reduction in less steady-state errors compared with other conventional methods of high-performance motor drives. Also, the real-time simulation is performed using Opal-RT OP4510. First we analyzed the results using software synchronized method, and the results also analyzed on digital oscilloscope using hardware synchronized method.